Around 400,000 years ago, in the forests of southern China, the largest primate our planet has ever produced was still alive. Gigantopithecus stood up to 3 meters tall, about 10 feet, and weighed as much as 295 kg, about 650 pounds. Its jaws were powerful enough to crush thick bamboo with ease, yet it was not a hunter. It survived on the forests themselves, feeding hour after hour in a world that had already shaped it into something with no equal. For nearly 2 million years, nothing challenged its place in these forests. Then another primate appeared. It was far smaller, carried simple stone tools, understood fire, and had begun looking at the world in a very different way. For at least 500,000 years, Homo erectus and Gigantopithecus shared the same landscape. They drank from the same rivers, crossed the same forest paths, and disappeared into the same shadows beneath the canopy. Almost everything we know about this giant survived by accident. Much of its fossil record was ground into traditional medicine long before science realized what those enormous teeth belonged to, leaving researchers to reconstruct the largest ape in history from only a handful of jaws and thousands of isolated teeth. Even today, one question refuses to settle. Did changing forests doom Gigantopithecus on their own, or did our ancestors arrive at exactly the wrong moment in its history? Today, we're uncovering the remarkable story of the greatest ape that ever lived, and the chain of events that brought its 2 million-year reign to an end. But before we do, if you're enjoying these deep dives into Earth's forgotten past, a quick like and subscribe really helps the channel grow and allows us to keep making documentaries like this. Now, let's step beneath the ancient forests of southern China. Nearly 2 million years ago, during the Pleistocene epoch, southern China and much of Southeast Asia offered a landscape that would surprise anyone expecting a frozen world. Monsoon rains returned with dependable rhythm, feeding forests whose crowns joined into an almost continuous ceiling of leaves. Light reached the ground in scattered patches where figs ripened, bamboo spread across hillsides, and broad-leaved plants crowded every opening. Food renewed itself across the seasons with remarkable consistency, creating one of the richest forest environments on Earth for animals able to live within its boundaries. Life filled every layer of this ecosystem. Early orangutans traveled through the upper branches, giant pandas searched dense bamboo stands, tapirs wandered among tangled vegetation, and deer species that have long since vanished browsed the forest floor. Countless birds, reptiles, and insects completed an intricate web that had developed across immense spans of time. Large herbivores prospered because the forest continually transformed sunlight and rainfall into leaves, stems, fruit, and shoots. In such surroundings, growing larger could become an advantage instead of a burden, granting access to greater feeding opportunities while reducing competition from smaller animals. Within this setting appeared Gigantopithecus blacki, a name meaning black's giant ape. The species honored Canadian paleoanthropologist Davidson Black, whose work on early human evolution in China shaped an entire generation of research. He passed away before the giant ape received its formal scientific description, leaving his name attached to one of the most extraordinary primates ever recognized. The title reflects both the animal itself and the scientific history surrounding its discovery. Its immense size often invites comparison with gorillas, although that resemblance reaches little farther than appearance. Evolution placed Gigantopithecus within the orangutan branch of the great ape family, a lineage that separated from the ancestors of modern orangutans between 10 and 12 million years ago during the Miocene. Across those millions of years, natural selection responded to forests, unlike any found in Africa. Dense Asian woodlands favor different feeding strategies, different movement through vegetation, and different solutions to survival. Every chapter of Gigantopithecus biology emerged from those conditions. That ancestry explains why the giant ape became so closely tied to closed canopy forests, fruiting trees, bamboo, and abundant understory plants shaped both its opportunities and its limits. The same environment that encouraged tremendous body size also narrowed the range of habitats where such a creature could flourish. Success became closely linked to ecological stability, with generations adapting ever more precisely to a forest that had rewarded consistency over flexibility. At the height of its distribution, Gigantopithecus occupied a broad region stretching across southern China, northern Vietnam, and parts of India. This range covered thousands of kilometers, which is about thousands of miles, of subtropical forest connected by favorable climate and abundant vegetation. Such a distribution suggests a species that was firmly established across much of eastern Asia, thriving wherever these productive woodlands remained connected. Long before changing climates began reshaping those landscapes, the giant ape stood as one of the defining inhabitants of an ecosystem that had already endured through countless generations of life. Few extinct animals have left behind such an unusual record. Nearly everything known about Gigantopithecus rests upon a collection of roughly 2,000 isolated teeth and only four partial lower jaws. From those scattered remains has emerged the story of an ape that towered over every other primate, even though no complete skull has ever been recovered. There are no hips to reveal its posture, no leg bones to measure its stride, no hands to hint at the strength of its grip, and no spine to trace the shape of its body. An entire giant has been reconstructed from the smallest surviving pieces. The reason lies within the caves where many of these remains accumulated. After a Gigantopithecus died, its skeleton often remained exposed before layers of sediment could protect it. During that interval, another resident of these cave systems arrived. Porcupines regularly gnaw bones to obtain calcium, an essential mineral for maintaining their continuously growing teeth. Research has shown that the long bones, ribs, vertebrae, and other skeletal elements of Gigantopithecus became part of that process, disappearing long before fossilization could preserve them. Tooth enamel resisted far more effectively because it is the hardest biological material produced by vertebrates, allowing those durable surfaces to survive while almost everything else vanished. Most discoveries have come from karst limestone caves scattered across Guangxi province in southern China, with additional finds extending into Vietnam and India. These caves acted as natural repositories across immense spans of time, collecting fragments from many generations of animals. Each newly examined chamber has expanded the record only slightly, adding another handful of teeth or another broken jaw to a collection that remains astonishingly incomplete for such an enormous species. Even so, every tooth carries an archive of information. The size of the molars allows researchers to estimate body mass through well established relationships between tooth dimensions and overall anatomy in living primates. Tiny scratches and pits across the enamel preserve evidence of food repeatedly crushed between opposing teeth. Microscopic silica structures from plants, known as phytoliths, sometimes remain attached to enamel surfaces, revealing which vegetation passed through those powerful jaws. Chemical signatures locked inside the enamel distinguish plants growing beneath forest canopies from those thriving in open landscapes, creating another layer of evidence for reconstructing diet. The teeth also preserve moments from individual lives. Fine grooves known as hypoplasia lines formed whenever growing enamel paused during periods of illness or limited nutrition, leaving permanent records of biological hardship. Growth lines within developing teeth reveal the pace of dental formation, offering clues about maturation and reproduction. Even molecules protected inside enamel crystals have endured across nearly 2 million years, preserving proteins that illuminate the evolutionary relationship between Gigantopithecus and modern orangutans with extraordinary clarity. It seems almost improbable that such confidence can emerge from evidence so fragmentary. Yet each isolated tooth contributes another sentence to a biography written across geological time. Without limbs, without a complete skull, and without a single fully preserved skeleton, science has assembled a portrait whose foundations rest upon enamel alone. Those enduring fragments have carried the memory of the largest primate ever known across hundreds of thousands of years, allowing its presence to return through patience, comparison, and careful observation. Every surviving tooth carries the imprint of a body that no longer exists. Like carefully preserved blueprints, these fragments reveal proportions, strength, and habits that vanished hundreds of thousands of years ago. Although the skeleton itself remains almost entirely absent, the architecture of the mouth preserves enough detail to reconstruct an animal whose feeding machinery exceeded that of every living great ape. The molars stand at the center of that reconstruction. They were broad, low-crowned, and covered by an exceptionally thick layer of enamel. Such a design excels at crushing and grinding plant material that resists ordinary chewing. Fibrous stems, hard seeds, woody tissues, and resilient vegetation all require repeated pressure before they can be swallowed. Every meal gradually polished the enamel into flattened working surfaces, producing patterns that match an animal adapted for long periods of powerful grinding instead of slicing or tearing. The mouth functioned like a biological mill, reducing stubborn plant matter into digestible pieces with remarkable efficiency. Supporting those teeth was an equally extraordinary lower jaw, deep and heavily reinforced. It provided extensive attachment areas for the temporal and masseter muscles, the major muscles responsible for closing the mouth. Scaling calculations based upon living great apes indicate that the resulting bite force may have reached several times that generated by a modern gorilla. Such strength was unnecessary for hunting or cracking bones. It reflected the mechanical demands of processing enormous quantities of resistant vegetation day after day across an exceptionally long lifetime. The front teeth tell a different part of the story. Gigantopithecus possessed small, closely packed incisors that resembled sturdy pegs more than cutting blades. Many primates rely upon broad incisors to peel fruit, strip leaves, or manipulate food before chewing. These reduced front teeth suggest a different approach. Food was gathered with the hands, brought directly to the mouth, then transferred toward the grinding molars with minimal preparation. The emphasis rested upon crushing instead of careful processing, a feeding style that matched the specialized anatomy farther back in the jaw. Its canine teeth also departed from expectations. In many living primates, long pointed canines serve as visual displays and effective weapons during conflicts between males. Gigantopithecus lacked such exaggerated structures. The canines remained comparatively blunt despite the animal's immense size. That pattern hints that physical stature itself may have carried much of the social message within the species. An individual standing above its rivals required little additional emphasis from oversized canine teeth, allowing natural selection to favor feeding efficiency over dramatic dental weaponry. Researchers have extended these anatomical clues beyond the mouth by comparing tooth dimensions with those of living great apes. Those relationships suggest an arm span exceeding 3.6 meters, which is about 11.8 feet, or nearly 12 feet. That is about 3.7 meters. Such breadth would have stretched wider than many small automobiles, reinforcing the impression of an animal built around tremendous reach and powerful upper limbs. Estimates also indicate marked differences between the sexes, with adult males likely approaching twice the weight of females, a pattern common among highly polygynous primates, where larger males gain greater reproductive success. Even signs of disease contribute another layer to this portrait. Several Gigantopithecus teeth preserve cavities formed through prolonged exposure to acidic sugars. Those lesions reveal that fruit remained an important seasonal resource, despite adaptations for grinding coarse vegetation. Together, every groove, surface, and imperfection transforms isolated teeth into an unexpectedly complete portrait, allowing the vanished anatomy of the largest primate ever known to emerge piece by piece from enamel alone. Size carries a price that cannot be escaped. Every hour of every day, a giant body must gather enough energy to keep muscles working, organs functioning, and cells alive. For Gigantopithecus, this invisible accounting shaped nearly every aspect of existence. Current estimates place its weight somewhere between 300 and 650 pounds, which is about 136 to 295 kilograms. The most recent findings, published during 2024, favor the upper end of that range, suggesting a body approaching 295 kilograms, which is about 650 pounds. Such mass demanded an extraordinary daily supply of food. Modern male gorillas weighing around 180 kilograms, which is about 397 pounds, may consume between 20,000 and 40,000 calories each day, almost entirely from vegetation. Scaling those energetic needs upward places Gigantopithecus in an entirely different category. It likely spent much of its waking life searching, feeding, chewing, and digesting, replacing the tremendous amount of energy required simply to remain alive. This dependence created what researchers describe as a metabolic trap. The giant ape could flourish only where food remained abundant throughout the year. Dense forests filled with edible plants offered the continuous harvest needed to sustain such an immense body. Wandering into open woodland or expanding grasslands would have offered too little nutrition for an animal carrying so much weight. Survival depended upon remaining inside one highly productive ecosystem whose resources rarely failed. Its movements reflected those demands. The available evidence points toward an animal that gathered food primarily across the forest floor, traveling steadily from one feeding site to another while covering broad areas in search of vegetation. Instead of brief meals, separated by long periods of rest, Gigantopithecus probably fed repeatedly across the day, processing large volumes of fibrous plants through the specialized jaws and teeth that had evolved for exactly that purpose. Each successful day depended upon maintaining a careful balance between calories gained and calories spent. Body size also limited where food could be reached. Modern orangutans can climb high into the canopy, moving through flexible branches to harvest fruit beyond the reach of many other animals. Gigantopithecus almost certainly lacked that option. Supporting hundreds of pounds among slender branches would have carried enormous mechanical risk. Even if climbing remained possible for younger or smaller individuals, sustained feeding high above the ground would have become increasingly impractical as body mass increased. A rich layer of food existed overhead, yet much of it remained effectively unavailable. This close relationship with the forest floor narrowed the giant ape's choices. Every adaptation that had once rewarded increasing size also reduced flexibility. The digestive system, feeding behavior, and immense musculature all relied upon uninterrupted access to dense vegetation growing at ground level. Any reduction in that dependable supply carried consequences that rippled through every part of its biology. For millions of years, those conditions remained favorable enough to support one of the largest primates ever to evolve. The balance appeared stable while the forests continued producing enough food to match its immense appetite. Beneath that long period of success, however, rested a dependence so complete that even modest environmental change would eventually expose the cost of becoming a giant. A meal disappears almost as soon as it is eaten, yet traces of it can remain for millions of years. Each bite leaves tiny marks, chemical signatures, and microscopic fragments that settle into tooth enamel with extraordinary persistence. By reading those durable records together, researchers have assembled an increasingly detailed picture of the daily menu that sustained the largest primate ever to walk the earth. One of the most revealing forms of evidence comes from phytoliths, microscopic silica structures produced within the cells of many plants. These tiny mineral bodies sometimes cling to tooth surfaces long after the surrounding plant tissue has vanished. Studies of Gigantopithecus teeth have recovered phytoliths consistent with members of the fig family, grasses, and vegetation closely associated with bamboo. Although each fragment is minute, together they point toward a forest diet built from a wide assortment of edible plants growing across the understory and surrounding woodlands. The chemistry preserved inside enamel tells the same story through another language. Carbon isotope measurements consistently indicate a diet composed almost entirely of plants using the carbon pathway typical of dense forests. Trees, shrubs, leaves, and shaded vegetation dominate this category, while grasses from open landscapes leave a distinctly different chemical signal. The enamel shows no meaningful evidence that Gigantopithecus relied upon open grasslands for food. Its nutritional world remained firmly rooted within productive forest ecosystems throughout its existence. Microscopic wear across the chewing surfaces provides another layer of evidence. Under powerful scanning electron microscopes, the enamel reveals countless scratches and pits created by repeated contact with resistant plant material. Those patterns match foods containing tough fibers and abrasive particles, including bamboo stems, bark, reeds, and similarly durable vegetation. Each meal gradually reshaped the enamel, producing a record that accumulated across years of feeding. The mouth functioned as an instrument built for endurance, repeatedly breaking down plants that demanded exceptional force before they could be digested. The presence of dental cavities adds an unexpected detail. Sugars found in ripe fruit encourage acid-producing bacteria that gradually erode enamel, leaving permanent holes within the teeth. Several Gigantopithecus specimens preserve exactly those lesions. They show that fruit formed a meaningful part of the diet whenever it could be obtained. Sweet seasonal harvests likely provided valuable energy, complementing the tougher vegetation processed during much of the year. Exactly how much bamboo the giant ape consumed remains an active subject of study. Some researchers consider bamboo its principal food source because of its dental structure and the environments where fossils occur. Others support a broader menu that included fruit, leaves, stems, bark, and possibly underground storage organs such as tubers. Recent research published during 2024 suggests that healthy populations displayed greater dietary flexibility before later individuals, increasingly depended upon lower quality foods as environmental conditions shifted. This combination of evidence creates an interesting parallel with the giant panda. Fossils of both species frequently occur within the same bamboo rich habitats, and both evolved powerful grinding teeth capable of handling fibrous vegetation. Their lives unfolded within similar ecological settings, drawing nourishment from forests that rewarded specialized feeding strategies while remaining highly dependent upon the continued stability of those habitats. One conclusion, however, stands with remarkable consistency across every line of evidence. Neither tooth shape, chemical composition, nor microscopic wear supports the idea that Gigantopithecus regularly consumed meat. The largest primate known to science built its immense body almost entirely from plants, relying upon forests that provided abundance through leaves, stems, fruit, and bamboo across countless generations. Among all the missing pieces of Gigantopithecus, none has inspired more discussion than the way it crossed its forest home. Teeth can reveal what an animal ate, how quickly it matured, and even moments of hardship during its life. They cannot reveal the rhythm of a stride. Without a pelvis, leg bones, feet, or vertebral column, every attempt to reconstruct its movement must begin with careful comparison instead of direct observation. This absence leaves researchers balancing probability against possibility. No complete postcranial skeleton has ever been recovered. There is no femur to measure the forces passing through the hip, no tibia to indicate weight bearing, and no foot bones to show whether the toes gripped branches or pressed against the ground. Each proposal must therefore rely upon living relatives and the mechanical limits imposed by an exceptionally large body. The interpretation favored by most researchers places Gigantopithecus on four limbs. Modern gorillas provide the closest comparison in overall size and body proportions, even though the two belong to different evolutionary branches. Supporting between 300 and 650 pounds, which is about 136 to 295 kilograms, on only two legs, would have placed extraordinary stress upon the hips, knees, and lower spine. Distributing that weight across both arms and legs through knuckle walking offers a more practical solution, reducing strain while allowing steady travel across uneven forest terrain. A different interpretation has persisted for decades, although it remains a minority view. The late researcher Grover Krantz argued that the shape of the lower jaw might indicate a more upright posture. Gigantopithecus possessed a broad jaw that widened toward the rear, creating enough internal space for the windpipe to pass comfortably while the skull rested above a vertical spine. In humans, this arrangement supports habitual upright walking. Critics note that jaw shape alone cannot determine posture, especially without the surrounding skeleton, yet the idea continues to illustrate how much information remains hidden with the missing bones. Movement itself was probably measured instead of hurried. Even a powerful body must obey the laws of mechanics. Each step required lifting tremendous weight before placing it forward once again. Long periods of feeding on the forest floor would have favored deliberate travel between productive feeding sites, conserving energy whenever possible. Brief upright postures, however, remain entirely plausible. Living gorillas and orangutans regularly stand on two legs for short intervals while reaching, displaying, or surveying their surroundings. Gigantopithecus almost certainly possessed similar flexibility, even if four-limbed travel remained its primary means of movement. Biomechanical models have produced another intriguing possibility. When scaling relationships from gorilla locomotion are applied to a much larger body, some calculations suggest that Gigantopithecus might have reached speeds approaching 47 kilometers per hour, which is about 29 miles per hour. Such estimates remain theoretical because they depend upon assumptions about muscles, joints, and limb proportions that cannot yet be verified. Without the missing skeleton, no calculation can move beyond informed approximation. What emerges from all available evidence is a picture defined by careful restraint. Gigantopithecus was probably a predominantly quadrupedal ape whose immense frame favored stable, energy-efficient movement across the forest floor. It could almost certainly rise upright for brief moments, yet its everyday progress likely unfolded through patient, deliberate steps that matched both its extraordinary size and the demanding world it inhabited. The forest gained a new resident, while Gigantopithecus still flourished among its familiar feeding grounds. Around 800,000 years ago, another ape entered the landscapes of Southeast Asia. It arrived carrying abilities unlike those of any other primate living there. This newcomer belonged to the species Homo erectus, and its appearance introduced a different way of surviving within the same world. Homo erectus combined physical endurance with growing intelligence. Some populations stood as tall as, or even taller than, many people living today. Their brains reached roughly 3/4 the size of modern human brains, providing greater capacity for planning, learning, and adapting to changing conditions. They traveled across remarkable distances, following rivers, forests, and open landscapes with a persistence unmatched by earlier members of the human lineage. Stone tools formed another defining characteristic. Carefully shaped hand axes, cleavers, and scrapers extended the usefulness of their hands, allowing them to process food, shape wood, and exploit resources in ways no other primate could achieve. Controlled fire added another layer to that expanding repertoire, altering daily life wherever it accompanied them. Evidence that these two remarkable species occupied the same landscape comes from several fossil localities, with one discovery standing above the rest. At Tham Cuyen Cave in Lang Son Province, northern Vietnam, researchers uncovered a deposit dating to approximately 475,000 years ago. Within the same accumulation lay teeth attributed to Homo erectus and Gigantopithecus blacki. They were not separated by continents or distant eras. Their remains entered the same cave system, preserving a direct record that both species inhabited the surrounding forests during the same period. Comparable discoveries from southern China reinforce that conclusion. Multiple fossil sites indicate overlapping distributions throughout the early and middle Pleistocene, revealing a long chapter of coexistence across Eastern Asia. These scattered records form a consistent pattern instead of isolated coincidence. The forests supported both species simultaneously, each following its own strategy while drawing life from the same landscapes. That overlap lasted for an astonishing span of time. Homo erectus reached the region around 800,000 years ago, while Gigantopithecus disappeared between 295,000 and 215,000 years ago. The result is a minimum of 500,000 years during which these two primates shared neighboring territories. That interval exceeds the entire existence of Homo sapiens so far, giving countless generations opportunities to encounter one another across forest paths, feeding grounds, and river valleys. To Gigantopithecus, the newcomer must have seemed unlike any creature previously encountered. It moved upright on two legs, carried shaped stones, and occasionally transported controlled fire through the landscape. Its body remained modest in comparison with the giant ape, yet its behavior differed from every other forest inhabitant. Curiosity, cooperation, and technology combined into a presence that could not easily be understood through instinct alone. From the perspective of Homo erectus, the encounter would have been equally extraordinary. Emerging from thick vegetation stood the largest primate ever known, reaching about 12 feet, which is about 3.7 meters, in height and possessing an arm span broader than many small automobiles. Every movement carried immense physical authority. The sound of such an animal passing through vegetation would have belonged to no familiar experience carried by the human lineage. For hundreds of thousands of years, two very different branches of the ape family occupied the same forests, each representing a separate answer to the challenges of survival in Pleistocene Asia. No witness remained to describe the first meeting between these two primates. Their story survives only through the patterns left by living animals, fossil evidence, and the ecological rules that shape how species share the same landscape. Although many details remain beyond recovery, those separate lines of evidence converge toward a picture that is surprisingly coherent. Everything known about Gigantopithecus suggests an animal with little interest in hunting. Its teeth, jaws, digestive adaptations, and chemical record all point toward a life centered on vegetation. A creature built for crushing fibrous plants had little reason to pursue moving prey. Homo erectus, like modern primates, almost certainly possessed the ability to distinguish between dangerous predators and large herbivores through repeated observation. After enough encounters, the giant ape would have become a familiar presence whose immense size inspired caution without necessarily signaling immediate danger. Most interactions were probably brief and uneventful. Large herbivores and smaller omnivores commonly occupy the same environments while focusing upon different resources. Gigantopithecus devoted much of its day to gathering plants across the forest floor, while Homo erectus expanded its diet through fruit, roots, smaller animals, and whatever additional foods could be obtained with tools. Their paths undoubtedly crossed, although direct competition for food remained limited because each species relied upon a different balance of resources. Distance itself likely became the preferred response whenever one group detected the other nearby. Observation, however, formed another part of the relationship. Homo erectus lived within organized social groups capable of sharing experience across generations. Individuals encountering the giant ape would have remembered where it fed, where it traveled, and which valleys or bamboo stands it visited repeatedly. Such knowledge carried practical value. A creature of that size influenced the surrounding landscape, creating predictable movement patterns that attentive observers could learn without approaching closely. Fire introduced a subtle change to those encounters. Controlled flames accompanied Homo erectus into places where natural fires had previously appeared only at irregular intervals. Living great apes display a natural reluctance to approach active fire, maintaining distance from heat, smoke, and flickering light. Gigantopithecus almost certainly shared that tendency. Campsites illuminated by burning wood may have altered the giant ape's movement, encouraging it to avoid areas where people gathered during evening hours. Such displacement required no violence. The presence of fire alone could gradually reshape how both species used portions of the same forest. Whether Homo erectus ever hunted Gigantopithecus remains one of the greatest uncertainties in this story. Direct evidence has never been discovered. Researchers have found no cut marks upon Gigantopithecus bones, largely because virtually no bones survived long enough to fossilize. No confirmed hunting site contains unmistakable remains of the giant ape. The missing skeleton leaves an important part of the evidence permanently beyond reach. Even so, another fact deserves equal attention. Across Africa and Asia, Homo erectus hunted remarkably large mammals, including rhinoceroses and elephants, using cooperation, planning, stone tools, and controlled fire. Against that background, an adult Gigantopithecus weighing as much as 650 pounds, which is about 295 kilograms, cannot be dismissed as an impossible target. Scientific caution, therefore, remains appropriate. Hunting may have occurred occasionally, or perhaps never at all. The evidence supports neither conclusion with certainty. What emerges most clearly is a landscape where two intelligent branches of the ape family recognized one another, adjusted to one another, and shared the same forests across hundreds of thousands of years. Some relationships in natural history are measured in moments. Others stretch across spans so immense that they reshape the character of an entire world. The shared existence of Homo erectus and Gigantopithecus belongs to the second kind. Their paths overlapped for at least 500,000 years, a duration greater than the entire existence of Homo sapiens as a distinct species. That single comparison changes how the forests of the Pleistocene are imagined. They were never occupied by one rising primate alone, but by several, each following a different evolutionary course beneath the same canopy. Those forests contained no predetermined winner. Gigantopithecus represented an ancient branch of the orangutan family that had become remarkably specialized within rich subtropical woodland. Homo erectus embodied another experiment, one driven less by physical size than by increasing behavioral flexibility. For countless generations, both strategies remained successful enough to persist together. The landscape carried room for each, provided the forest continued supplying the conditions upon which their lives depended. Their greatest difference lay beyond anatomy. It existed in the pace at which each species responded to change. Homo erectus could modify behavior within a lifetime. Useful discoveries spread through observation, imitation, and teaching, allowing entire communities to benefit from the experience of a few individuals. Across thousands of years, these accumulated adjustments steadily transformed how people gathered food, used tools, explored unfamiliar terrain, and organized daily life. Gigantopithecus followed another rhythm. Like living great apes, its responses were guided chiefly by instincts, refined across immense evolutionary intervals. Adaptation occurred through natural selection acting over hundreds of thousands of years, not through rapidly expanding traditions. Such a strategy had succeeded for millions of years while forests remained abundant. Yet environmental challenges, arriving faster than biological evolution could respond, created a widening gap between the giant ape and its increasingly adaptable neighbor. Living beside Gigantopithecus would also have provided Homo erectus with valuable practical knowledge. Communities occupying the same valleys could recognize where the great ape preferred to feed, which fruiting trees attracted repeated visits, and how its movements shifted with changing seasons. They could learn which bamboo stands supported the largest individuals and how the animals reacted when smoke or flames appeared nearby. Such observations carried immediate importance for travel, resource gathering, and avoiding unnecessary encounters. Knowledge preserved through spoken tradition became another survival tool, handed from experienced adults to younger generations. This remarkable duration of coexistence has inspired another possibility that reaches beyond bones and stone tools. Some researchers have proposed that repeated encounters with an enormous forest ape over 500,000 years may have entered the cultural memory of early human communities. Stories describing an immense human-like creature living deep within Asian forests appear across many regions. These traditions emerged far later than Gigantopithecus itself, and no evidence demonstrates a direct connection. Even so, The length of coexistence leaves open the intriguing possibility that distant memories, reshaped through countless generations of oral storytelling, retained faint echoes of an animal once encountered by forgotten ancestors. Whether that idea ultimately proves correct or remains speculative, the broader lesson endures. For hundreds of thousands of years, more than one intelligent primate lineage shared the forests of Asia. One relied upon extraordinary physical scale, refined through deep evolutionary time. The other depended increasingly upon learning, cooperation, and cultural inheritance. Their long companionship reminds us that the Pleistocene was shaped by parallel stories unfolding together, each revealing a different path through the same living world. For millions of years, the forests of southern China and Southeast Asia had followed a dependable rhythm. Rain arrived with familiar regularity, streams continued their patient course, and fruit ripened across the canopy in patterns that changed little from one generation to the next. Countless creatures evolved within that dependable cycle, their bodies shaped by a world whose abundance seemed almost permanent. Around 600,000 years ago, that long stability began to give way to a different pattern, subtle at first, yet carrying consequences that would echo through every layer of the forest. The transformation would have appeared modest on a geological timescale. Mountains remained where they had always stood, rivers still crossed the valleys, and the forests did not disappear overnight. Instead, the seasons grew increasingly distinct. Wet months delivered generous rainfall, while dry intervals lingered longer than before. The separation between those seasons widened, interrupting the continuous production of leaves, flowers, and fruit that had sustained one of the largest primates ever to exist. Evidence gathered from the recent nature study reveals this transition with remarkable clarity. Researchers examined pollen preserved within sediments collected from 22 cave sites across southern China. Those microscopic grains formed an enduring archive of changing vegetation. Layer by layer, they recorded the gradual replacement of dense, fruit-rich, closed canopy forests by woodlands that became more open and increasingly seasonal. The change unfolded over many thousands of years, offering little sign of sudden catastrophe, yet steadily altering the ecological balance upon which countless species depended. This distinction is important. The forests did not immediately become open grasslands. Their character shifted in smaller increments. Fruit-bearing trees still flourish during favorable periods, though dependable harvests no longer stretched across the entire year. Months that once offered continuous nourishment gradually developed intervals when preferred foods became scarce. The forest still appeared alive and productive, although its generosity now arrived according to a stricter calendar. The endless banquet had acquired periods of absence. Different animals responded according to their abilities. Orangutans possessed lighter bodies and retained exceptional climbing skills, allowing them to search high within the canopy for scattered fruit, tender leaves, or other resources beyond the reach of ground-dwelling competitors. Their flexibility allowed them to adjust as familiar food sources became less predictable. Smaller mammals also shifted diets or expanded their foraging ranges without demanding enormous quantities of energy each day. Gigantopithecus faced a far narrower path. Its immense body required an extraordinary intake of vegetation, while its size prevented sustained movement through the upper branches where valuable foods still remained. Most feeding occurred across the forest floor, where seasonal shortages became increasingly severe. Every dry interval forced longer searches for nourishment, demanding more energy precisely when fewer calories could be gathered. The challenge deepened with each recurring season, gradually tightening an ecological constraint that offered little opportunity for escape. Nothing in this changing landscape announced the approaching decline with dramatic finality. Trees still shaded the valleys, bamboo continued growing in many places, and familiar animal calls carried through the woodland. Yet the foundations supporting Gigantopithecus had begun to shift beneath the surface. A forest that once matched every requirement of its remarkable biology had become less dependable, asking for adaptability from a species whose evolution had invested instead in extraordinary size and enduring specialization. Evolution often reveals its deepest lessons through close relatives whose paths slowly separate. Among all comparisons surrounding Gigantopithecus, none offers greater insight than the one shared with the orangutan. Their story began along the same branch of the primate family tree, with both descending from a common ancestor approximately 10 to 12 million years ago. They occupied the forests of Asia, depended upon many of the same plants, and evolved beneath the same changing skies. In the end, one lineage endured, while the other disappeared, leaving behind a remarkable study in how different solutions to the same environment can produce opposite destinies. The resemblance between them extended beyond ancestry. Both belong to the orangutan lineage rather than the African great apes. Their jaws, teeth, and dietary preferences reflected millions of years spent adapting to subtropical forests rich in fruit, leaves, and other plant foods. Each lineage developed features suited to extracting energy from woodland vegetation. Yet evolution continued shaping them in different directions, gradually widening the contrast until their responses to environmental change became almost completely opposite. Modern male orangutans may weigh as much as 90 kilograms, which is about 198 pounds. Even at that impressive size, they remain the largest animals capable of living almost entirely among the upper branches of tropical forests. Powerful arms, flexible joints, and extraordinary balance allow them to travel through the canopy with remarkable efficiency. When fruit becomes scarce near the ground, they climb toward higher branches where blossoms, young leaves, seeds, or overlooked fruit may still provide nourishment. Their world extends through many vertical layers of the forest rather than a single level. Gigantopithecus carried no such advantage. Its immense frame, estimated between roughly 300 pounds and 650 pounds, transformed climbing from an everyday activity into an overwhelming mechanical challenge. Branches capable of supporting smaller primates offered little security beneath such weight. The richest foods remaining high above the forest floor gradually became unreachable. As seasonal shortages spread through the woodland, entire portions of the available food supply existed beyond the physical limits imposed by its own remarkable size. Dietary flexibility widened the contrast even further. Field studies have shown that orangutans consume more than 400 different kinds of food over the course of changing seasons. Fruit may dominate during favorable periods, yet bark, leaves, flowers, insects, seeds, and other resources become valuable substitutes whenever preferred foods decline. This broad menu allows survival through years that might otherwise prove devastating. Every additional food source represents another opportunity to endure temporary hardship without exhausting precious energy reserves. Evidence preserved within the teeth of Gigantopithecus suggests a more restricted pattern. Fruit remained important whenever it was abundant, while fibrous vegetation provided dependable nourishment during ordinary conditions. The recent nature study indicates that healthy populations displayed some dietary flexibility before environmental conditions deteriorated. As forests became increasingly seasonal, however, the giant ape relied more heavily upon lower quality fallback foods. Its available choices narrowed as the landscape itself narrowed, reducing resilience precisely when greater adaptability became essential. There is a quiet irony within this shared ancestry. The same evolutionary lineage produced two extraordinary primates whose greatest strengths pointed in opposite directions. One mastered movement through the highest branches by remaining comparatively light and behaviorally adaptable. The other achieved unmatched physical scale, perfectly suited to an environment that remained stable across immense spans of time. When that stability gradually faded, the qualities that had once made Gigantopithecus so successful became the very limits it could no longer overcome. Some of the clearest chapters of prehistory are preserved in the smallest places. A fossil tooth, no larger than the end of a finger, can retain a lifetime of biological history. Enamel forms gradually during growth, and, once complete, it does not remodel or heal. Every interruption remains fixed within its surface. Long after muscles vanish and bones crumble, those narrow markings continue carrying a record of seasons that were generous and seasons that demanded more than the body could provide. Among the most revealing of these features are structures known as dental hypoplasia. They appear as narrow grooves or shallow lines crossing the enamel, created when the specialized cells responsible for building teeth temporarily slow or stop their work. Such interruptions can arise during periods of malnutrition, disease, or prolonged shortages of food while a young individual is still developing. Much like the growth rings of a tree preserve evidence of difficult years, these markings become permanent reminders that normal growth was interrupted before eventually resuming. The recent Nature study examined these stress markers across Gigantopithecus teeth collected from different ages of the species. The pattern that emerged was remarkably consistent. Earlier populations displayed fewer interruptions, suggesting that growing individuals generally developed under dependable environmental conditions. Later populations told another story. As forests became increasingly seasonal and dependable food declined for longer stretches of each year, the number of hypoplasia lines rose. Individual animals experienced repeated episodes during which their developing bodies struggled to secure enough nourishment for ordinary growth. Those markings transform an environmental change into a deeply personal record. They reveal that young Gigantopithecus did not merely inhabit forests that were becoming less productive. They lived through recurring periods when their bodies diverted limited resources away from building healthy enamel because immediate survival demanded higher priority. Each line represents a moment when growth paused, leaving behind evidence that endured for hundreds of thousands of years after the animal itself disappeared. Chemical evidence preserved within the same teeth strengthens that conclusion. Carbon isotope measurements continue to indicate reliance upon plants characteristic of dense forests throughout the decline of the species. At the same time, microscopic wear and additional dietary evidence suggest that preferred foods became less dependable. Fruit contributed less frequently to the daily diet, while tougher fallback resources such as bark, stems, reeds, and other fibrous vegetation became increasingly important. These foods occupied the stomach and reduced immediate hunger, yet they delivered substantially less usable energy for every mouthful consumed. The combination carried profound biological consequences. Gigantopithecus already required an immense daily supply of calories to sustain its extraordinary body size. Every reduction in nutritional quality forced longer hours of feeding while providing smaller energetic returns. Juveniles growing within this increasingly demanding environment experienced the greatest burden, since development required resources beyond those needed for ordinary maintenance. Their teeth preserved the evidence long before the species reached its final decline. By the time the youngest individuals recorded repeated interruptions in their enamel, the process leading toward extinction had already been unfolding across many generations. The changing forest did not erase Gigantopithecus in a single dramatic moment. It gradually reduced the reliability of food, narrowed dietary opportunities, and left each successive generation carrying a slightly heavier biological burden than the one before. Those burdens remain visible today, etched into enamel that still speaks with remarkable clarity across immense spans of time. Every species carries within its life cycle an invisible rhythm. Some multiply with remarkable speed, replacing losses almost as quickly as they occur. Others follow a slower pattern, investing years into each new generation. Gigantopithecus belonged to this second path, one shaped by patience rather than abundance. While such a strategy could flourish in a dependable world, it depended upon stability that would not last forever. Among living primates, the orangutan provides the closest comparison. Female orangutans produce offspring at intervals of roughly 7 to 9 years, the slowest reproductive pace known among living mammals outside our own lineage. Each infant demands prolonged care, learning, and protection before reaching independence. Fossil evidence preserved within the developing teeth of Gigantopithecus suggests a similarly prolonged pattern of growth. The spacing of microscopic growth lines inside the enamel indicates that teeth formed gradually, pointing towards slow maturation and a life history centered upon raising few young with substantial parental investment. Biologists describe this pattern as the strategy of species that thrive where survival is normally dependable. Instead of producing many offspring with little care, each juvenile represents an enormous investment of time and energy. In forests that remained productive through the passing seasons, such an approach offered clear advantages. Young individuals could mature over many years, while parents relied upon predictable food supplies. Population numbers remained stable because losses occurred gradually, and births, though uncommon, were sufficient to replace them. The balance shifted once dependable seasons disappeared. Each successful birth required years before another could follow. If changing forests reduced food availability, weakened developing juveniles, or prevented some young from surviving until adulthood, replacement slowed below the pace of loss. A female producing one infant, roughly every 8 to 10 years, could not compensate for repeated failures across an increasingly difficult landscape. Even modest increases in juvenile mortality carried consequences that accumulated across generations instead of disappearing with the passing years. The arithmetic behind such a decline appears almost gentle at first glance. There is no sudden collapse, no dramatic plunge within a handful of seasons. Imagine that only half of the offspring survived long enough to reproduce during the prolonged environmental deterioration. Each generation would become slightly smaller than the one before. Adults growing old would disappear more quickly than new adults entered the breeding population. Every cycle reduced opportunities for future births, creating a decline that steadily reinforced itself without requiring any single catastrophic event. A difficult decade could not be repaired within the lifetime of one generation. A difficult century became vastly more damaging. Thousands of years of recurring shortages gradually thinned populations until neighboring groups occupied forests separated by increasing distances. Encounters between unrelated adults became less frequent, reducing opportunities to exchange genes and establish healthy breeding populations. Small groups became increasingly vulnerable to disease, accidents, and ordinary fluctuations that larger populations could have absorbed with little consequence. The fossil record reflects precisely this gradual unraveling. Gigantopithecus did not vanish in one dramatic moment. Evidence instead suggests a prolonged reduction extending across many thousands of years as suitable forests contracted into scattered refuges. The final populations likely occupied isolated patches that no longer supported the social and reproductive connections their ancestors once maintained. The same deliberate life history that had served the species for immense stretches of time ultimately prevented it from recovering once the pace of environmental change exceeded the pace at which new generations could replace those that were lost. Every fossil species reaches a point where its traces become fewer, then rarer still, until the record ends. That final appearance is never a single moment preserved in stone. It is the last surviving clue that happened to endure while countless others vanished with time. For Gigantopithecus, modern research has narrowed that fading interval more precisely than ever before, revealing when the greatest primate finally disappeared from the forests it had occupied for millions of years. The most comprehensive reconstruction came from the Nature study published during 2024. Researchers examined evidence collected from 22 cave sites distributed across southern China, combining luminescence dating of cave sediments with fossil pollen, enamel chemistry, and other environmental indicators. Together, these independent records converged upon the same conclusion. Gigantopithecus blacki disappeared sometime between approximately 295,000 and 215,000 years ago. Instead of relying upon isolated discoveries, the investigation assembled a regional timeline that traced both the changing forests and the gradual retreat of the species across its remaining range. That conclusion transformed the long accepted explanation for its disappearance. Earlier interpretations suggested that Gigantopithecus endured until dense forests gave way to extensive grasslands. Such a dramatic landscape shift appeared an obvious point of extinction. The new evidence tells a different story. The widespread transition toward open grassland occurred only after the giant ape had already vanished. By the time those sweeping environmental changes unfolded, the species was no longer present to experience them. Its decline, therefore, belongs to an earlier chapter, one written through gradual ecological deterioration instead of sudden transformation. The canopy remained standing across much of the region, yet seasonal patterns altered the availability of fruit and other dependable foods. Each dry interval lasted longer. Preferred resources became less reliable. Nutritional stress accumulated over generations, while dietary flexibility narrowed and reproductive recovery slowed. None of these changes appeared dramatic when viewed within a single lifetime, although together they steadily reduced the ability of populations to endure. Evidence indicates that the final survivors occupied the richest remaining forests of what is now Guangxi. These refuges retained the dense vegetation capable of supporting the demanding biology of Gigantopithecus longer than surrounding regions. Even so, isolated habitat patches carried their own burdens. Small populations exchanged fewer individuals, reducing genetic diversity and limiting opportunities for successful breeding. Each remaining refuge became increasingly separated from the next, turning what had once been a continuous population into scattered remnants. The closing stage left remarkably little spectacle for the geological record to preserve. There is no evidence for a catastrophic volcanic eruption a sudden disease sweeping across the forests, or a single climatic disaster ending the lineage in one generation. The disappearance unfolded gradually enough that each generation may have seemed little different from the one before, even as total numbers continued slipping downward across many thousands of years. Then the record falls still. Teeth that once appeared regularly within cave deposits cease to appear. The pathways worn across forest floors vanished beneath new growth. Feeding grounds passed into other lives. Without ceremony or visible finality, the largest primate known to science crossed beyond the reach of the fossil record. The forests continued changing after its departure, carrying forward only the enduring evidence left inside stone and enamel. Some discoveries arrive as a single fossil lifted from stone. Others emerge only after thousands of separate observations are assembled until an older picture can no longer stand. The reconstruction of Gigantopithecus followed the second path. Across years of fieldwork, laboratory analysis, and collaboration between specialists, fragments scattered across southern China gradually aligned into the clearest account ever produced of the giant ape's final chapter. The study, published during 2024 in the journal Nature, was led by geochronologist Kira Westaway of Macquarie University in Sydney. She worked alongside researchers from the Chinese Academy of Sciences, Southern Cross University, the Max Planck Institute for Geoanthropology, and several additional scientific institutions. Each group contributed a different piece of the investigation, creating an unusually broad partnership capable of examining the question from many directions instead of relying upon a single line of evidence. Its scale distinguished it from every previous attempt. Scientists investigated evidence preserved within 22 cave sites distributed across southern China. Sediment layers were dated through luminescence techniques that measured when mineral grains had last been exposed to light. Fossil pollen reconstructed changing plant communities across the landscape. Stable isotope analysis of tooth enamel revealed shifts in long-term diet. Dental hypoplasia recorded episodes of developmental stress experienced by growing individuals. For the first time, these independent records were woven into one continuous timeline instead of being interpreted separately. That unified chronology revealed an unexpected pattern. The decline of Gigantopithecus began around 600,000 years ago, considerably earlier than researchers had once believed. During that interval, the forest still appeared extensive across much of the region. Nothing resembling a dramatic ecological collapse had yet occurred. Even so, the combined evidence showed that subtle environmental changes had already begun reducing the reliability of food resources, placing sustained pressure upon populations long before the landscape underwent more obvious transformation. The study also clarified why those early changes proved so damaging. No single factor explained the extinction on its own. Instead, three biological pressures reinforced one another across many generations. Seasonal drying created recurring gaps in fruit availability. Exceptional body size prevented Gigantopithecus from reaching food sources high within the forest canopy when conditions on the ground became less dependable. At the same time, a slow reproductive rate limited the species' capacity to replace declining numbers. Each challenge strengthened the next until recovery became progressively less likely. One of the most revealing comparisons came from another great ape occupying the same forests. Orangutans experienced the same changing climate, yet their populations persisted. Evidence indicates that they broadened their diet, exploiting a wider assortment of available foods as seasons became more pronounced. Their lighter bodies also allowed continued access to the upper canopy, where additional resources remained available. The contrast suggested that ecological flexibility, more than simple endurance, separated survival from disappearance. Even after assembling this remarkable body of evidence, one important uncertainty remained. The chronology overlaps with the presence of Homo erectus across the same landscapes, leaving open the possibility that interactions occurred over many generations. Yet correlation alone cannot establish cause. Gigantopithecus is known almost entirely from teeth and a handful of jawbones, leaving virtually no skeletons that might preserve unmistakable traces of hunting or butchery. The study therefore strengthened the environmental explanation while acknowledging that the influence of Homo erectus cannot presently be measured with confidence, leaving that question suspended between evidence and possibility. The final chapter of Gigantopithecus carries an uncertainty that no fossil has yet resolved. Across southern China and parts of Southeast Asia, two remarkable primates occupied the same broad landscape for an extraordinary span of time. Homo erectus had arrived around 800,000 years ago. Gigantopithecus vanished sometime between 295,000 and 215,000 years ago. Their histories remained intertwined for at least 500,000 years, ending only when one lineage continued and the other faded from the record. The chronology itself invites careful thought, yet the evidence demands restraint. Climate records reconstructed from cave sediments, fossil pollen, and chemical signatures preserved within enamel indicate that environmental change had already begun undermining Gigantopithecus around 600,000 years ago. Seasonal food shortages became increasingly common while the forests still appeared extensive across much of the region. This gradual decline was already unfolding before Homo erectus had become numerous enough across the landscape to represent a dominant ecological force. Every major line of evidence points toward climate-driven habitat change as the principal cause that set the extinction in motion. Even so, the final stages of the story unfolded under different conditions. By then, Gigantopithecus populations appear to have been confined to scattered forest refuges where dependable food remained available. Groups were likely smaller, more isolated, and less capable of recovering from additional losses. Under those circumstances, influences that might once have been minor could suddenly carry greater consequence. A species already reduced by environmental pressure possesses little margin for absorbing new challenges. One possibility concerns hunting. Evidence from Africa and Asia demonstrates that Homo erectus possessed the cooperation, planning, and technology required to kill animals far larger than themselves. Fossil sites preserve traces of large mammals, including rhinoceroses and elephants, processed by groups of these early humans. Against that background, a giant ground-dwelling ape would not have represented an impossible target. Fire, sharpened wooden spears, and coordinated behavior created opportunities unavailable to any earlier primate lineage. Yet this remains a possibility rather than a demonstrated event. No Gigantopithecus bones preserve cut marks, and almost no skeletons exist to examine for such evidence in the first place. Another explanation requires no direct confrontation at all. Homo erectus consumed a varied diet that included fruits, edible plants, and other forest resources. During seasons when fruit became scarce, every remaining patch of productive woodland gained greater importance. If both species relied upon overlapping food sources within shrinking habitats, competition alone may have increased the burden carried by Gigantopithecus. A population already surviving close to its energetic limits could decline further without a single deliberate hunt taking place. Science therefore arrives at a measured conclusion instead of a dramatic verdict. The strongest evidence identifies changing climate and diminishing ecological flexibility as the foundation of the extinction. Human influence cannot be dismissed, particularly during the final generations when surviving groups occupied scattered refuges. At the same time, it cannot be confirmed with the evidence presently available. That uncertainty deserves preservation rather than embellishment. Some extinctions leave unmistakable traces of violence, others leave only fragments, dates, and landscapes altered across immense spans of time. Gigantopithecus belongs to the second kind of story, where the greatest lesson comes from recognizing the boundary between what the fossils reveal and what they still keep beyond our reach. There was no moment when the forest announced that something immense had departed. No boundary marked the final day of Gigantopithecus. Seasons continued their familiar rhythm. Rivers crossed the same valleys, and new leaves unfolded where old ones had fallen. The absence settled gradually into the landscape until it ceased to feel like a recent loss and became the ordinary condition of the world that followed. By around 250,000 years ago, Homo erectus had become an increasingly capable inhabitant across broad regions of Asia and Africa. Fire was no longer an occasional curiosity, but a practical companion in many places, extending activity beyond daylight and altering the relationship between people and their surroundings. Stone tools had grown more refined through countless generations of shared experience, producing carefully shaped hand axes, cleavers, scrapers, and other implements suited to different tasks. Many researchers also suggest that these populations possessed forms of proto-symbolic behavior and perhaps a basic spoken language, allowing knowledge to pass with growing precision from one generation to the next. This steady accumulation of learning distinguished Homo erectus from every earlier member of the human lineage. Individual discoveries no longer vanished with the individuals who made them. Useful behaviors could persist, spread, and improve across thousands of years. Each generation inherited more than genes alone. It also inherited experience, expanding the ability of communities to respond to changing environments without waiting for biological evolution to produce new adaptations. Across the forests of southern China, life continued with remarkable diversity. Orangutans still occupied suitable woodland, moving through the canopy in search of seasonal foods. Gibbons crossed the upper branches with effortless speed. Macaques foraged across varied habitats, adapting readily to shifting conditions. Even within this rich community, however, something fundamental had changed. The largest non-human primate ever to inhabit Earth no longer shaped the structure of the ecosystem. For roughly 2 million years, Gigantopithecus had been part of these forests. Its disappearance altered the balance of life in ways no surviving fossil can fully measure. The remarkable aspect of this transition is that the world left behind by Gigantopithecus was still not the world of our own species. Homo sapiens would not appear across Asia for many tens of thousands of years. Forests, rivers, and mountains still belonged to communities that modern people would never witness directly. The stage had changed, yet the principal actor of later human history had not arrived. Even so, the broader direction had already become visible. The strength of Homo erectus rested less in physical size than in cumulative learning, cultural transmission, and behavioral flexibility. Those qualities allowed adaptation to proceed across lifetimes instead of waiting through immense spans of evolutionary change. Once that process gathered momentum, it became an increasingly influential force within every landscape the species entered. The disappearance of Gigantopithecus therefore marked more than the ending of a remarkable ape. It also foreshadowed a pattern that would echo repeatedly through later prehistory. As members of the human lineage became more capable, large primates and many forms of megafauna faced growing pressures alongside environmental change. The first chapter of that long story had already been written, leaving the forests permanently altered long before modern humanity stepped into them. Long before paleontologists assigned a scientific name to the largest ape that ever lived, its teeth had already begun another journey. They passed from limestone caves into baskets, from traders into apothecary shops, and from shelves into finely ground powders. Their identity was unknown, yet they were far from unnoticed. Across parts of East Asia, these fossils were known simply as longu, or dragon bones, remnants of creatures imagined through tradition rather than prehistory. For centuries, traditional Chinese medicine regarded fossilized bones and teeth as valuable natural materials. They were crushed into powder and prepared as remedies for a wide variety of ailments, including tooth pain, disorders affecting the skeleton, and recurring fevers. Their usefulness rested within an established medical tradition rather than an understanding of their geological origin. The remarkable size and unusual appearance of certain teeth inspired curiosity, though no scientific framework yet existed to explain the animals from which they had come. The limestone landscapes of Guangxi contained abundant cave systems where fossil deposits accumulated across immense spans of time. As local communities gathered fossil material from these caves, Gigantopithecus teeth entered commercial networks alongside the remains of many other extinct animals. Generation after generation, enormous molars disappeared into medicine markets. Each one carried information about a vanished species, yet that information was gradually erased as the fossils were ground into powder and consumed. By the time scientific attention finally reached these collections, the loss had already become impossible to measure. An unknowable number of Gigantopithecus specimens had vanished forever before anyone realized their significance. Extinction had removed the living animal hundreds of thousands of years earlier. Human activity, undertaken with entirely different intentions, reduced much of the surviving fossil evidence as well. The species experienced a second disappearance, this time from the physical record that might have revealed its history. An unexpected realization transformed the search for prehistoric life. Early paleontologists discovered that valuable fossils were often concentrated not at excavation sites, but within apothecary shops. These businesses had become accidental repositories, gathering material collected from caves scattered across distant regions. Instead of beginning every investigation with a shovel, researchers learned to examine medicine markets where countless fossil fragments had already been assembled through ordinary trade. Among those scientists was Gustav Heinrich Ralph von Koenigswald, whose visits to Chinese pharmacies reshaped the understanding of Asian prehistory. During the middle of the 20th century, an extraordinary shipment containing 47 Gigantopithecus teeth drew particular attention. Tracing the origin of those fossils led researchers back to Liu Cheng Cave in Guangxi. There, systematic excavation produced the first Gigantopithecus lower jaw ever recovered, providing the anatomical evidence needed to move beyond isolated teeth and begin reconstructing the animal itself. There is a quiet elegance within this unlikely chain of events. The people who collected, traded, and prepared these remarkable teeth recognized that they were unlike ordinary bones. They preserved them because they believed they possessed value, even though the explanation they inherited belonged to legend rather than evolutionary history. Without intending to do so, Generations of apothecaries safeguarded enough evidence for science to rediscover a creature otherwise destined to remain unknown. In the end, dragon bones became something even more extraordinary than dragons. They became fragments of a forgotten world, carried across centuries by human hands until the questions surrounding them finally found answers rooted in deep time instead of myth. History sometimes changes through a moment so ordinary that it almost passes unnoticed. A customer examines a shelf. A shopkeeper arranges jars. Among countless fossil fragments resting inside a Hong Kong pharmacy, one enormous tooth waited for the person capable of recognizing that it belonged to a world no one had yet imagined. Ralph von Koenigswald, a German-Dutch paleontologist working primarily on Homo erectus discoveries in Java, had developed an unusual habit. Instead of relying only on excavations, he searched apothecary shops throughout East Asia. Medicine markets often gathered fossil material collected from distant limestone caves, creating collections assembled through commerce rather than scientific fieldwork. Each visit carried the possibility that an unfamiliar specimen might reveal the location of an unexplored fossil deposit. During 1935, that possibility became reality. While examining piles of dragon bones offered for traditional medicine, von Koenigswald noticed a single molar unlike any tooth he had encountered before. It did not resemble a human tooth. It did not resemble the teeth of any known great ape. Its proportions suggested an animal that exceeded every established expectation. In the middle of an ordinary pharmacy, surrounded by fossils destined to become powder, an entirely unknown branch of primate history announced itself through a single piece of enamel. The tooth measured about 20 millimeters by 22 millimeters, a size roughly comparable to a human thumbnail. No primate molar of such dimensions had ever been documented. Even before identifying the species, the scale alone implied a remarkable body size. Every ridge, basin, and polished surface recorded years of chewing, preserving anatomical details that allowed comparison with living and extinct apes. Careful study revealed familiar relationships hidden within unfamiliar proportions. The overall structure of the tooth resembled members of the orangutan lineage, sharing characteristic patterns in its enamel and crown shape. At the same time, every measurement extended far beyond anything known from orangutans or other living primates. The conclusion emerged gradually, yet convincingly. This tooth represented a giant ape, unlike any species previously recognized by science. Von Koenigswald responded by establishing an entirely new genus, Gigantopithecus, meaning giant ape. He named the species blacki in honor of Davidson Black, the respected anatomist whose pioneering work on Peking man had transformed the understanding of early human evolution before his death the previous year. The name linked one extraordinary fossil discovery with another, preserving the memory of a colleague whose influence continued beyond his lifetime. The search did not end with that remarkable purchase. During the following 4 years, von Koenigswald returned repeatedly to pharmacies across Hong Kong and southern China, eventually acquiring 3 additional Gigantopithecus teeth. Each specimen strengthened the case that an immense unknown ape had once inhabited the forests of southern China. Then the Second World War interrupted his research. Captured as a prisoner of war in Java, he reportedly protected precious fossil casts by hiding them inside milk bottles buried beneath the ground until the conflict ended. There is remarkable symmetry in the story's beginning. The largest primate ever known entered scientific history without a dramatic excavation, towering skeleton, or spectacular cave chamber. Its first introduction came through a medicine shop, a scientist trained to notice unusual teeth, and a forgotten fossil rescued moments before it could disappear forever. A fragment of enamel can preserve a story that no skeleton is able to tell. Long after flesh has vanished and bone has dissolved into the surrounding earth, the hardest tissue ever produced by a vertebrate may still guard tiny traces of the molecules that once helped build a living body. Within one fossil tooth of Gigantopithecus, those traces endured across almost 2 million years. In 2019, a research team led by Frido Welker at the University of Copenhagen published a landmark study in the journal Nature. Working with tooth enamel from Gigantopithecus blacki that dated to approximately 1.9 million years ago, the researchers successfully extracted and sequenced preserved proteins. At the time, this represented the oldest protein sequence ever recovered from a primate fossil. The achievement extended molecular evidence far beyond what many scientists had believed possible, reaching into a chapter of evolution that had previously been accessible only through anatomy and geology. The discovery depended on the unusual nature of enamel itself. Unlike bone, which is porous and continually remodeled during life, tooth enamel forms once and remains remarkably stable. Its tightly packed crystalline structure surrounds microscopic remnants of the proteins involved in its creation, shielding them from many of the chemical processes that gradually erase biological material. Across immense spans of time, this mineral barrier acts as a durable archive, preserving fragments that can still be identified long after almost every other organic tissue has disappeared. When those ancient protein sequences were compared with living great apes, the result brought striking clarity. They matched most closely with modern orangutans. The similarities were stronger than those shared with gorillas, chimpanzees, or humans. Earlier anatomical studies of the teeth and jaws had already suggested that Gigantopithecus belonged within the orangutan branch of the great ape family. The molecular evidence independently arrived at the same conclusion, strengthening a relationship that had once rested almost entirely upon fossil form. Those proteins also carried information about deeper history. By comparing the accumulated differences between living orangutans and the preserved Gigantopithecus sequences, researchers estimated that their evolutionary lineages separated roughly 10 to 12 million years ago during the Miocene. At that time, great apes occupied forests stretching across parts of both Asia and Africa, diversifying into several branches whose descendants would eventually follow very different paths. One branch produced the adaptable orangutans that still survive today. Another led toward the immense ape, whose story survives through scattered teeth and a handful of massive jaws. Even with this remarkable success, molecular evidence has firm boundaries. Proteins cannot reveal the color of Gigantopithecus hair or the expression carried across its face. They cannot show the rhythm of its movement through the forest, the shape of its hands in motion, or the sound of its voice beneath the canopy. Molecular sequences establish ancestry with remarkable confidence, yet they remain unable to reconstruct appearance, behavior, or daily life. The enamel therefore speaks with precision, though never with completeness. It confirms kinship across millions of years, while leaving many other chapters unwritten. Each preserved protein narrows uncertainty about where Gigantopithecus belonged upon the great family tree, even as the vanished skeleton continues to withhold countless details, allowing the largest ape ever known to remain partly concealed within the enduring endurance of stone. The greatest mystery surrounding Gigantopithecus is not concealed within some undiscovered cave waiting for future explorers. It was likely erased long before fossilization had the opportunity to preserve it. The missing skeleton is not merely an unfortunate gap in the record. It is the predictable outcome of a process that unfolded across countless generations within the limestone caves of southern China. Those caves sheltered more than giant apes. They also became home to porcupines, animals with an unusual nutritional habit. Their continuously growing incisors required constant wear, and their bodies demanded minerals that were often difficult to obtain from plants alone. Bones offered an abundant source of calcium. Paleontologists studying the cave deposits of Guangxi have found extensive evidence of gnaw marks left by porcupines on the remains of many large mammals. Before sediments could bury and protect exposed skeletons, these persistent scavengers gradually reduced them piece by piece. The timing mattered as much as the feeding itself. After an animal died, its bones often remained exposed on the cave floor for months or years before layers of mud, dust, and mineral deposits sealed them away. During that interval, scavengers had unrestricted access. Long bones, ribs, vertebrae, and the broad surfaces of the pelvis provided rich material for gnawing. Each visit removed another fragment until little remained. By the time burial finally occurred, the skeleton had already been dismantled. Teeth followed a different fate. Enamel is the hardest biological material produced by any vertebrate, far more resistant than ordinary bone. The thick portions of the lower jaw also possessed exceptional durability. These structures endured repeated chewing that destroyed more fragile elements. Their dense mineral composition allowed them to survive weathering, scavenging, and burial with far greater success. As a result, the fossil record preserved the parts that even determined bone eaters struggled to consume, while much of the rest disappeared. This unequal preservation has shaped every scientific discussion of Gigantopithecus. Researchers possess hundreds upon hundreds of massive teeth and several impressive lower jaws, yet they have no confirmed pelvis, femur, tibia, complete skull, or vertebral column. Without those bones, fundamental aspects of the animal remain uncertain. The exact proportions of its body, the details of its walking posture, the size of its brain, and many features of its face cannot be reconstructed with confidence. Careful comparisons and informed estimates remain possible, though complete certainty probably never will. That absence gives Gigantopithecus a distinctive place within the fossil record. Many extinct animals are known from nearly complete skeletons that reveal how they moved, stood, and interacted with their surroundings. This giant ape is understood through scattered pieces that survived because they happened to resist destruction more effectively than everything around them. Scientific knowledge advances from what remains, while continually acknowledging the larger story carried away long ago. There is a quiet elegance in that outcome. The largest primate ever to walk the earth left behind no towering skeleton to greet future generations. Instead, its enduring monument consists of roughly 2,000 teeth, each once shaped for crushing hard vegetation and enduring endless meals. Against remarkable geological odds, those same teeth outlasted flesh, bone, climate, and time itself, becoming the small but resilient fragments that continue to speak for an animal whose greatest features have almost certainly vanished forever. Some extinctions leave bones, others leave stories. Long after Gigantopithecus vanished from the forests of Asia, accounts of enormous human-like creatures continued to appear across mountains, valleys, and dense woodlands. Whether those traditions preserved distant echoes of genuine encounters or emerged through other cultural pathways remains impossible to determine, yet the resemblance has intrigued scientists for many decades. The connection did not begin with modern popular culture. In 1960, Zoologist Vladimir Chernesky published a short paper in the journal Nature examining a famous photograph of unusual footprints taken in the Himalayas during 1951. After studying the spacing and apparent gait, he suggested that the tracks were more consistent with the movement expected from Gigantopithecus than with a human or a bear. The proposal remained speculative, built upon limited evidence, yet it demonstrated that respected researchers considered the extinct giant ape a possible inspiration for enduring legends. Geography also encouraged the comparison. Fossils show that Gigantopithecus occupied parts of southern China, northern Vietnam, and India, regions bordering or lying close to the great mountain systems where Yeti traditions later flourished. Orangutans once ranged much farther across mainland Asia than they do today and survived alongside early members of the human lineage until roughly 10,000 years ago. Encounters with several kinds of large apes across immense spans of time may have supplied recurring images that different cultures reshaped into their own local traditions. The scale of human memory adds another layer to the discussion. Homo erectus shared portions of Asia with Gigantopithecus for roughly 500,000 years. Much later, populations of Homo sapiens entered landscapes already occupied by communities, carrying generations of accumulated knowledge about the animals around them. Oral traditions can preserve fragments of remarkable events across astonishing lengths of time, although they change with every retelling. Any direct connection between those traditions and Gigantopithecus can no longer be tested, yet the possibility illustrates how natural history and cultural memory sometimes travel side by side. Within China, one enduring example is the Yeren, often translated as the wild man. Reports describe a heavily built, shaggy creature moving through remote forests and mountain valleys, especially within Hubei and Sichuan. Witnesses have variously portrayed it as upright, powerfully built, and covered in hair. Such descriptions naturally invite comparison with a giant ape, although folklore also gathers features from imagination, local beliefs, mistaken identification, and the ordinary tendency of stories to grow with time. Scientific evidence, however, establishes a firm boundary between legend and paleontology. Gigantopithecus is considered extinct. No verified fossils younger than approximately 215,000 years have been discovered, despite decades of intensive exploration. There is no credible evidence that the Yeti, Bigfoot, or similar creatures represent surviving populations of this remarkable ape. Even so, the persistence of giant ape traditions across Asia remains worthy of reflection. Communities separated by geography and history preserved narratives about imposing forest dwellers without knowledge of fossil discoveries that would emerge much later. Those legends do not prove that Gigantopithecus endured beyond its time. They reveal something different, that encounters with extraordinary animals can leave impressions lasting far longer than the animals themselves, carried through memory after the living creatures have disappeared from the world. A forest is never shaped by a single creature, no matter how immense. During the Middle Pleistocene, the woodlands of southern China formed a living network in which countless species influenced one another through feeding, movement, competition, and the steady exchange of energy. Gigantopithecus occupied only one place within that web, yet its extraordinary size gave it a role unlike any other primate before or since. The same landscape supported giant pandas, already adapted to bamboo-rich habitats that stretched across valleys and limestone hills. Tapirs wandered the forest floor, browsing leaves and tender shoots while following paths worn through generations of travel. High above them, ancestors of today's orangutans moved among the branches with a flexibility that later proved essential to their survival. Stegodon, an extinct relative of modern elephants, passed through these forests as another immense plant eater, reshaping vegetation with every journey. Hyenas, ancestral deer, and early sun bears completed a community that balanced countless relationships across seasons that repeated for hundreds of thousands of years. Around 800,000 years ago, another presence became part of this world. Homo erectus established populations across portions of Asia, carrying fire, increasingly sophisticated stone tools, and behaviors passed between generations through observation and practice. These early humans entered an ecosystem that had already been functioning for immense spans of time. They encountered forests whose rhythms had been established long before their arrival, sharing the landscape with animals that had evolved together across changing climates. Gigantopithecus almost certainly influenced its surroundings in ways extending beyond its own survival. An animal of such scale would have pressed trails through dense vegetation with repeated movement. Fruit swallowed in one part of the forest could have carried seeds to another before passing through the digestive system. Feeding on branches and sturdy plants likely opened patches within thick growth, allowing sunlight to reach lower vegetation and creating opportunities for other species. None of these effects required intention. They emerged naturally from the daily life of an enormous herbivorous ape moving through its habitat year after year. When Gigantopithecus disappeared, the forest did not lose every familiar sound or every recognizable inhabitant. Trees continued growing, streams continued winding through limestone valleys. Pandas remained within bamboo stands, orangutans persisted in suitable habitats, and countless smaller creatures carried on with lives largely unchanged. Even so, one ecological role had vanished. The greatest terrestrial primate, a presence that had shaped this environment for nearly 2 million years, no longer contributed to the continual exchange between animal and landscape. Nature rarely leaves an empty place waiting to be filled. Ecosystems adjust through countless small responses that unfold across generations. Other species expanded or contracted according to their own abilities, while the influence once exerted by Gigantopithecus dissolved into history. The forest continued forward without replacing exactly what had been lost. Among all the members of that vanished community, the giant panda remains the most familiar to modern eyes. It still depends upon bamboo-rich forests, still faces pressures created by changing environments, and still illustrates how specialized lifestyles can become vulnerable when landscapes shift beyond their limits. Across immense stretches of time, that enduring survival echoes the broader history of the forest itself, preserving one recognizable thread from a community whose largest primate exists today only through fossils, scientific evidence, and the enduring traces left within Earth's long memory. Success can carry the seeds of its own ending when the world changes around it. For nearly 2 million years, Gigantopithecus occupied forests that rewarded enormous size with remarkable consistency. Generation after generation inherited bodies shaped by an environment rich enough to support them until the largest primate in Earth's history became the natural outcome of millions of years of favorable selection. Within those productive forests, being larger offered undeniable advantages. A massive body discouraged most potential predators and allowed individuals to dominate feeding areas on the forest floor. Greater physical strength reduced competition with smaller herbivores, while substantial energy reserves could help endure brief periods when favored foods became less abundant. With relatively stable habitats extending across southern China, natural selection repeatedly favored the traits that had already proven successful. Those same traits became increasingly costly as the climate shifted in subtle but persistent ways. Every increase in body mass demanded more daily nourishment. A giant that had flourished amid dependable harvests now required extraordinary quantities of food during seasons when fruit became less predictable. Dependence upon abundant vegetation slowly transformed from an advantage into a narrowing constraint, binding survival to habitats that no longer provided the same reliability. Body size also shaped where food could be gathered. Gigantopithecus appears to have relied primarily upon resources available near the ground, including tough vegetation and seasonal fruit. Smaller apes retained access to the upper canopy, where additional foods remained available during leaner months. As seasonal shortages lengthened, reaching those elevated resources became increasingly important. The physical design that once suited Gigantopithecus so well offered little opportunity to exploit that higher layer of the forest. Reproduction introduced another challenge. Large mammals generally mature more slowly, produce fewer offspring, and invest greater care in each young individual. Such a strategy succeeds when adult survival remains high and environmental conditions remain dependable. Once populations begin shrinking, however, recovery becomes increasingly difficult. Each loss represents a larger share of the remaining breeding population, while opportunities to restore former numbers unfold only across many generations. Movement across changing landscapes also became more demanding. A smaller, more flexible primate could travel farther, exploit varied habitats, and respond more readily as familiar forests became fragmented. Gigantopithecus carried the momentum of an enormous body through terrain that gradually offered fewer connected refuges. Expanding into distant regions became progressively less practical as suitable habitat retreated into scattered pockets. Evolutionary biologists describe the final stage of this process as an extinction vortex. Declining numbers reduce genetic diversity. Smaller populations become more vulnerable to inbreeding and chance events. Environmental pressures continue acting upon an already diminished species, making recovery increasingly improbable with each passing generation. No single step guarantees extinction. Together, they create a reinforcing cycle that steadily narrows the remaining possibilities. During much of this same period, Homo erectus followed a contrasting path. Smaller bodies required fewer calories. An omnivorous diet provided greater flexibility. Cultural learning allowed successful behaviors to accumulate across generations, while broader ecological tolerance opened opportunities unavailable to highly specialized species. These qualities did not make early humans stronger in any simple sense. They made them adaptable. The story of Gigantopithecus therefore reaches beyond the rise and fall of one remarkable ape. Evolution favors traits that match present conditions, never future ones. In forests that remained generous, immense size represented triumph. In forests that gradually became less predictable, the same inheritance became a burden, revealing that survival often belongs to those able to change as readily as the world surrounding them. The forests that once supported Gigantopithecus did not lose every branch of the great ape family. As climates shifted across the Pleistocene, several relatives continued their own journeys through changing landscapes, carrying different solutions to the same challenge. Their histories reveal that survival did not follow a single path. It emerged through many forms of flexibility, each shaped by millions of years of evolution. Chimpanzees developed one of the broadest ecological toolkits among living apes. Their communities feed on fruit, leaves, seeds, insects, honey, and small animals, adjusting their diet as seasons change. They fashion sticks to gather termites, stones to crack hard nuts, and modify behaviors through observation of one another. Such cultural traditions allow knowledge to accumulate across generations, giving each population practical responses suited to its own environment instead of depending upon inherited instinct alone. Gorillas offer a different example. Adult males may weigh as much as 180 kilograms, which is about 397 pounds, making them the largest living primates. Their strength is remarkable, yet they remain considerably smaller than Gigantopithecus is believed to have been. That difference carries important consequences. Gorillas feed upon well over 100 plant species, moving between forest layers as opportunities change. Leaves, stems, shoots, fruit, and bark all contribute to a diet capable of shifting with seasonal availability, reducing dependence upon any single resource. Orangutans preserve another branch of this shared family story. Molecular evidence places Gigantopithecus closest to their lineage, suggesting a common ancestor that lived many millions of years earlier. While their giant cousin increasingly relied upon life near the forest floor, orangutans retained an existence among the canopy. Their lighter bodies allowed access to fruit beyond the reach of larger ground-dwelling animals. During difficult seasons, they adjusted their feeding behavior, expanding the range of foods they could exploit until richer harvests returned. Human ancestors carried flexibility even further. Homo erectus gradually expanded beyond familiar forests into grasslands and varied environments, supported by cultural learning, controlled fire, cooperative behavior, and increasingly sophisticated stone tools. Each generation inherited more than physical traits. It also inherited accumulated experience. Adaptation no longer depended solely upon genetic change unfolding across countless generations. Practical knowledge could spread within a lifetime, allowing populations to respond to changing conditions with remarkable speed. That trajectory continued through later members of the human lineage until people occupied deserts, tropical forests, frozen coastlines, high mountains, and eventually traveled beyond Earth's atmosphere. No other ape has matched that ecological reach. The foundation of this expansion rested less upon physical strength than upon learning, cooperation, communication, and the continual refinement of shared ideas. Seen together, these surviving lineages illuminate the absence left by Gigantopithecus without diminishing its extraordinary success. For nearly 2 million years, it flourished within an ecosystem that rewarded specialization on an immense scale. The changing Pleistocene gradually favored different qualities. Broad diets proved more dependable than narrow ones. Flexible behavior offered more possibilities than rigid routines. Smaller bodies demanded fewer resources when forests became less predictable. Across the fossil record, each surviving ape preserves a different answer to the same enduring challenge. None escaped change. Each endured by meeting it with enough versatility to remain part of the living world. Gigantopithecus followed another path, magnificent within its own time, yet bound to conditions that could no longer sustain it. The forests continued without their largest inhabitant, while the more adaptable branches of the ape family carried the story forward. There are moments in Earth's history that seem fixed only because they have already happened. Looking backward, the disappearance of Gigantopithecus can appear almost unavoidable, as though every step of its long existence pointed toward the same ending. The fossil record tells a gentler story. It suggests a future that narrowed through circumstance, where another path remained possible until the landscape itself changed direction. For nearly 2 million years, the forests of southern China provided the conditions this remarkable ape required. Those woodlands expanded and contracted across countless generations. Rainfall shifted, temperatures drifted, and familiar plant communities rose and fell. Gigantopithecus endured through each variation, preserving its place within the ecosystem for a span of time that exceeded the entire history of our own species. Such endurance speaks of resilience rather than fragility. The climatic changes that eventually reshaped its world were substantial, yet they were not unmatched within Earth's deeper history. Comparable fluctuations had unfolded before without ending the lineage. This time, seasonal dryness became more persistent, forests broke into scattered patches, and dependable food became increasingly difficult to predict. Each pressure alone might have been manageable. Together, they arrived in a sequence that steadily reduced the margin separating persistence from disappearance. If those environmental shifts had unfolded even 200,000 years later, or if seasonal extremes had remained less pronounced, the outcome might have been different. Gigantopithecus could have continued occupying the forests until Homo sapiens reached eastern Asia. Human history would then have begun alongside another giant member of the ape family, one encountered through observation instead of imagination. Such an animal would have differed greatly from the towering figures of popular fiction. It would have spent much of its life searching the forest floor for nourishing plants, moving with deliberate purpose through bamboo stands and mixed woodland. Communities living nearby would almost certainly have recognized its habits, its favored feeding grounds, and the seasons when encounters became more common. Artists might have carved its likeness into stone. Travelers could have described it in careful detail. Natural philosophers would have debated its place among living creatures long before modern evolutionary science emerged. That possibility lends another dimension to extinction. Species do not always vanish because they are poorly adapted or fundamentally inferior. Gigantopithecus remained one of the most successful primates ever to evolve, flourishing across an immense stretch of geological time. Its disappearance followed the convergence of environmental change, ecological specialization, and limited flexibility, all arriving within the same interval. Fortune, measured across millions of years, can become as influential as strength. Every surviving organism occupies the present through a similar chain of fortunate continuities. Countless ancestors endured droughts, volcanic winters, shifting continents, unfamiliar competitors, and changing climates. Remove one favorable season or alter one migration route, and an entirely different collection of species might inhabit the Earth today. Evolution shapes opportunity, yet opportunity also depends upon conditions no lineage can control forever. The story of Gigantopithecus therefore reaches beyond one remarkable ape. It reminds us that existence unfolds within windows that open and close across deep time. Every species lives inside such a window, sustained while circumstances remain compatible with its way of life. Those openings have never belonged permanently to anyone, and they never will. Across the immense sweep of its existence, Gigantopithecus stood as the largest primate ever to walk the earth. Generation after generation inherited a world that rewarded extraordinary size. Dense forests supplied abundant vegetation, broad jaws processed enormous quantities of food, and no predator regularly challenged a healthy adult. Every visible sign pointed toward success. Within its own habitat, the giant seemed perfectly established, as though such dominance could continue without limit. Its story reveals a quieter truth about evolution. Dominance and resilience are not interchangeable. An organism may become exceptionally well suited to one set of environmental conditions while gradually losing the capacity to endure different ones. The qualities that make a species flourish during long periods of stability can narrow the range of futures available when the surrounding world begins to change. Gigantopithecus depended upon productive forests with dependable plant resources. Its immense body required substantial nourishment every day, and that demand remained constant, regardless of shifting rainfall or changing seasons. As woodlands became increasingly fragmented, the giant could not reduce its needs in proportion to the shrinking landscape. Every decline in food availability carried greater consequences than it would have for a smaller, more flexible neighbor capable of exploiting different habitats and a broader range of foods. The fossil record repeats this lesson through many other remarkable creatures. Megatherium, the giant ground sloth of South America, reached extraordinary proportions before disappearing near the close of the Pleistocene. The woolly mammoth flourished across cold northern grasslands until environmental transformation and human expansion narrowed its remaining refuge. Diprotodon, the immense marsupial, often called the giant wombat, once wandered Australia before vanishing from that continent. Paraceratherium, the hornless giant rhinoceros that remains the largest known land mammal, also belonged to a world whose conditions eventually disappeared. Each giant achieved tremendous success within its own ecological setting, yet none carried an advantage that remained universal across changing ages. These histories do not suggest that evolution steadily favors smaller bodies. Size itself is neither reward nor mistake. It is one possible solution among countless others, shaped by the opportunities available at a particular moment in Earth's history. When those opportunities persist, immense bodies may thrive for millions of years. When they fade, the same adaptations can become increasingly difficult to sustain. The contrast with the human lineage emerges from this principle rather than from physical comparison. Smaller bodies demanded fewer resources. Omnivorous diets expanded available food. Cultural learning allowed useful behaviors to spread far more rapidly than genetic change alone could accomplish. Flexibility accumulated alongside intelligence, offering responses to unfamiliar circumstances that specialists could not always match. The remains of Gigantopithecus, therefore, preserve more than evidence of an extinct ape. They preserve a pattern repeated across geological time. Specialists often become masters of the worlds that shaped them, yet mastery remains inseparable from the continued existence of those worlds. When environments shift beyond familiar limits, previous success offers no lasting guarantee. That perspective reaches naturally into the present. Human activity is altering forests, rivers, climates, and coastlines at an accelerating pace. The fossil record contains countless examples of species whose adaptations matched landscapes that later transformed beyond recognition. Gigantopithecus now stands among those enduring reminders, showing that greatness in one chapter of Earth's history can depend entirely upon conditions that another chapter no longer provides. One branch of the great ape family now occupies an unusual place in Earth's history. While countless relatives have vanished and those that remain face mounting pressure, Homo sapiens has expanded across nearly every continent, carrying its influence into environments far beyond the forests where its distant ancestors first evolved. That position did not emerge through separation from the rest of the ape family. It grew from the same shared ancestry that once included Gigantopithecus. Today, every other living great ape confronts an uncertain future. Chimpanzees, bonobos, gorillas, and orangutans all survive within shrinking ranges, their populations reduced by habitat loss, hunting, disease, and the accelerating transformation of natural landscapes. The family that once filled tropical forests with many different forms has become increasingly narrow until only one lineage continues to expand while the others struggle to persist. The contrast carries an unusual symmetry. The same flexibility that helped the human lineage endure changing climates during the Pleistocene eventually became the capacity to reshape entire ecosystems. Fire, agriculture, cities, industry, and global trade all emerged from minds capable of solving immediate problems while steadily altering the wider world. Forests that developed across millions of years can now disappear within a handful of human generations. Among the surviving apes, orangutans hold a particularly meaningful place. Molecular evidence identifies them as the closest living relatives of Gigantopithecus. Their ancestors and the giant ape shared a common lineage that reached back into the Miocene, before each followed its own evolutionary path. Today, those remaining cousins occupy fragments of forests across Southeast Asia, where expanding agriculture, logging, climate change, and continuing human development steadily reduce the landscapes upon which they depend. The pressures differ in detail from those that confronted Gigantopithecus, yet the underlying pattern carries a familiar rhythm. Specialized habitats become less stable, available space contracts, and recovery grows increasingly difficult. The fossil record cannot provide instructions for the future, yet it preserves consequences with remarkable clarity. It shows ecosystems responding to changing climates, species flourishing within favorable conditions, and extinctions following when those conditions disappear. Gigantopithecus belongs to that record, preserved through teeth and fragments of jaw that outlasted the forests that once sustained them. Its remains describe what happened without assigning purpose or blame. Our own position differs in one important respect. Unlike every earlier species represented in stone, humans possess the ability to study those vanished worlds and recognize recurring patterns. We can compare climates, separated by millions of years, reconstruct extinct ecosystems, measure present environmental change, and understand that living communities depend upon conditions that can be altered or preserved through collective choices. Even with that knowledge, certainty remains beyond reach. The future cannot be excavated from rock. It unfolds through decisions made one generation after another, shaped by circumstances that continue to evolve. Awareness alone does not guarantee wisdom, just as intelligence alone has never guaranteed permanence. Gigantopithecus walked through forests without any understanding that the balance sustaining its world was gradually changing. Its story reached its conclusion without witness or memory until fossil evidence restored a small part of what had been lost. We stand in a different moment. The forests still speak through living apes, as well as ancient teeth, and the record they preserve is no longer hidden from those willing to read it. There is no monument marking the place where the final Gigantopithecus lived its last days. Somewhere within the forests of southern China, between approximately 295,000 and 215,000 years ago, the last member of its species moved through a landscape that had already become smaller and less dependable than the one known by generations before. The forest still offered shelter, yet each passing season carried fewer of the conditions that had sustained this giant lineage for nearly 2 million years. What remains seems impossibly small beside the life it represents. About 2,000 teeth have been recovered, scattered across 16 cave sites, and, before their scientific value was recognized, mixed into the grinding bowls of forgotten traditional pharmacies. 4 partial lower jaws endured alongside them. No complete skull has ever emerged from the earth. No arm or leg bones have appeared. No complete skeleton waits beneath untouched stone, ready to answer every remaining question. The outline of the largest primate ever known has been assembled from fragments that survived where almost everything else disappeared. Another trace endured in an entirely different form. Proteins, preserved inside enamel, carried a molecular memory reaching back more than 10 million years, revealing the shared ancestry between Gigantopithecus and the orangutan lineage. That relationship remained hidden for immense stretches of time before chemistry uncovered what bones alone could never fully explain. Evolution left part of its history written within the hardest tissue the body could produce. Memory also traveled along another path, one shaped by people rather than fossils. Tales of towering forest beings, the Yeren, the Yeti, and other giant figures continued to pass from one generation to another across parts of Asia. Science does not recognize these stories as surviving populations of Gigantopithecus, yet their persistence reminds us that remarkable animals often leave impressions extending beyond their physical remains. Long after an organism vanishes, echoes of encounters can continue within culture, growing and changing as centuries unfold. The limestone towers of Guangxi still rise above the forests. Rain still moves through the valleys, and trees continue to spread new leaves from roots linked to landscapes of immense age. Many of those living forests descend from ecosystems that once nourished Gigantopithecus. The giant itself is absent, while the setting that shaped its existence continues to renew itself one season after another. Science gathered this story through remarkable patience. Teeth revealed diet, cave sediments preserved chronology, enamel protected ancient proteins. Missing bones shaped understanding as surely as recovered fossils. Piece by piece, an animal that seemed almost impossible to know regained its place within Earth's history, carrying weight, ancestry, ecological purpose, and an existence stretching across nearly 2 million years. The largest primate ever to walk the Earth is known chiefly through the tools it used to eat. It shared part of the world with our ancestors, vanished without leaving the complete skeleton generations of researchers hope to find, and entered the deep archive of life with extraordinary restraint. Its jaw survives as a distant outline, its lineage continues through living relatives, and its presence lingers wherever the story of giants is told. That enduring presence may be the closest thing any extinction leaves behind.